This is part 2 in a set of slides about maximum and minimum values. The basic idea is to look at optimization. That's the big goal. That's section 4.7. And the real focus of this will be to look at this idea of a constraint. And that's going to change some of the recipes that we've been looking at a little bit so far. But just to review a little bit of stuff, critical numbers, that's the spot where f prime is equal to 0 or f prime doesn't exist. Those spots are highlighted here. These spots will usually, but don't always, have to correspond to local minimum points or local maximum points. What's interesting is actually this line segment where all the points, at least in the middle here, correspond to both local mins and local max points if you look at the definition. Although these 2 points at the end are only local minimum points but not local maximum points because, well, this point's not a local maximum point because you need all of the nearby y values to be smaller, but the y value over here is bigger. Okay, likewise, if you just change this graph just a little bit over on this side, you can still highlight the x values, or rather the points that correspond to x values, which are critical numbers. You could, I guess, call these critical points. And now this point over here, let's see, these are local mins and maxes, but this point over here is just a local max, this point over here is just a local min. Okay. And finally, just as another little bit of review, another place you could get a critical number, another way you can have a local minimum or maximum is this kind of point right here. This is a local minimum, even though the derivative doesn't exist right here. So that's a second way to get a local minimum. And as an example, you could take this function to find the critical numbers. Well, this is a polynomial, so always differentiable, so you won't find that kind of critical number, but the other kind of critical number where f prime is equal to 0, take the derivative, get that f prime. So we're trying to look for x value c such that f prime is equal to 0. So you take the derivative here, set this formula equal to 0. So the solution to x squared minus x minus 6 equals 0 after factoring is this. So x is equal to -2 is a critical number, and x is equal to 3 is a critical number. You could also just maybe stare at the graph of this particular function shown here to get critical numbers. There are 2 critical numbers where f prime is equal to 0 and 3 critical numbers corresponding to points where f prime doesn't exist because these are sharp, pointy parts of the graph. Just to review a little bit more, there are local maximum points right here and here. They're actually coincidentally the points which are in red. They don't always have to be, but a balloon would get stuck there and would get stuck there. This point is actually not the global maximum point, though. There is no global maximum because there are points along here that have bigger y values. These 3 points down here, they are local minimum points. They also they're local minimum points because rainwater will get stuck there and there and there. But they are also global minimum points because no point on this graph has a smaller y value. Just to review, here's the definition of critical number, and the recipe for local or relative min and max points is just to find those x values c, which are critical numbers, but it's possible that you could find this sort of x value which is a false x value, and it's not a helpful x value, but that's okay. It just kind of comes along for the ride. It's one extra x value, no big deal. This was the final version of the relative max point or relative min point or local max point or local min point finding formula recipe, but the recipe for global or absolute max and min points, this is not quite right yet. We're going to fix that in just a moment, but we'll just look at this example right here. So here's another function, identify the local max points and min points. This point over here is also the global max point. The coordinates, just through some computer software you can find, they're right here. The book's terminology is to say that 3.03 is the global maximum, and that f has a global maximum at negative 1.07057. So that's how the book will talk about the x values. Now, I want to take a look at this example again, but with a constraint. So if you restrict the x values a little bit, that'll chop the function. So here's the constraint right here. Sorry that the numbers are not that great, but what this ends up doing is all these interesting points we had before are basically the same, but now there's actually a point, due to the chopping, there's a point with a smallest y value. There's a lowest point in the graph, and so this is the global minimum point. You might ask, is this a global minimum, is this a local minimum point now due to chopping? And it's not according to the terminology in our book. This point is as well, likewise, not a local minimum point. Okay, so we have a global max point as before, same point as before, but we also have a global minimum point now, this point over here. Let's just look at one other example. So what we just saw was a global minimum point on the end point. It occurred at this end point. And in the next, and the thing is, this global minimum point was not a local minimum point, and our local minimum point finding recipe would not have found this point because the slope is very steep here. It's not 0. And that's why if you see this part just drawn in dotted, this was the part of the graph that we just chopped off. And so our method currently does not detect this point. So that's a problem. One more example of this. This is actually example 4 in the book on page 275. Just label a couple important points in here. And now you can just see from the picture, let's just identify a couple things. Here's some local minimum points. There's a local maximum point. These are not considered local maximum points according to this book. Take a look at that parenthetical remark in example 4 in the book. However, this point does have the biggest y value, so that's the global maximum point. So the previous example saw a global minimum point at the end point of an interval. Here we see a global maximum at the endpoint, and the global minimum is actually somewhere in the interior, it's somewhere inside of this interval, namely at the x value of 3. So the real point of these two examples is that a global maximum or a minimum can end up occurring not just somewhere on the inside where our methods currently detect it, namely to find the derivative set equal to 0 or see where the derivative doesn't exist, but once you chop, if you just chop, due to chopping, our method doesn't find anything because it would appear that the graph would continue going like this without chopping, and the slope here is not 0. And so our method currently of take derivative set equals 0 doesn't find this point. So our current global max-min point finding recipe is not quite right. We should not just find the critical numbers, but also do one additional thing, which is check the boundaries. See what happens at the left endpoint at x is equal to a, see what happens at x is equal to b. All this essentially does is give you 2 extra x values to check in addition to the x values you found before, and whichever x value corresponds to the biggest y value is the global max, and whichever x corresponds to the smallest y value is the global min. This is called the closed interval method. It basically works like this. This just spells out what's inside the book, just a little bit more detail. And the reason that the closed interval method always gives you something is due to the extreme value theorem. We'll use this theorem once in section 5.3 in the book, but the function does have to be continuous in order to have a global maximum and to have a global minimum. This function right here, for instance, if you look at x values a little bit less than 2, you keep getting bigger and bigger y values, but you never get a biggest y value. Right? So there's no global maximum, because as soon as you think you have a point that would be the global maximum, just go halfway to this open circle, and you get another point which has a bigger y value. This theorem requires a closed interval, so take a look at the graph of tangent, and you have bigger and bigger y values as you get closer and closer to pi over 2. The interval does need to be bounded. You can't just look at the function x squared defined on all the real numbers, because you get bigger and bigger y values. But once you chop this thing, once you say you're only going from x is -1 to 1, then there's a global minimum point and a global maximum point. So let's try doing this on this particular function. Find the global maximum and minimum using the closed interval method on the interval -2 to 1. So this is an x value interval. What are the critical numbers? Step 1. Well, f is differentiable everywhere. Take the derivative. You could actually see that from this formula, because no matter what x you plug in, you'll get a number out of this. But set this thing equal to 0, and the only solution to this will end up being x is equal to 0. Since x is 0 is the only critical number, what you do now is look for the y value there, and the corresponding y value is equal to 1. And that's it for step 1, but in the closed interval method, you also have to look at the x value of -2 and the x value of 1. And all you do is at the x value of -2, what the book calls a, just plug that in, get the corresponding y value out, which is e to the -4. Look at the other x value at the other endpoint of 1, plug into this formula right here, get e to the -1 for that. So now you have three y values, 1, e to the -4, and e to the -1. Compare those. The biggest is 1, and the smallest is e to the -4. And you can see everything here working out on the graph too. So the global maximum occurs right here, the global minimum occurs over here. Okay, here's another example. In this particular function, the thing to look at for critical numbers is a place where there might be non-differentiability. That's the thing to really worry about when you have absolute values. So where do you look? This function f happens to not be differentiable at 1. How do you really check? you check by taking this input here to absolute value, which is x minus 1, set that equal to 0. And that's the spot, most of the time, 99% of the time, when a function that has an absolute value would not be differentiable. So the solution to x minus 1 is equal to 0 is 1. Everywhere else, the derivative is defined. The only x value then that's a critical number is 1. You compute the corresponding y value, plug in f of 1, and you'll get 2. And then step 2 is to check the endpoints. Right? So check at the x value negative 2, what's the y value? You get that. At the x value of 3, b is equal to 3, get the y value by plugging in 3 into x over here, and you get 0. So now take these three y values, 2, negative 1, and 0, and ask which is biggest. It's 2, so that's the global maximum. What's the smallest of those three numbers here? It's negative 1, so that's the global minimum. And here's a graph. We'll skip the next example. It's basically the same idea. It's just the interval is a little different, but the formula for the function is the same. The point here is that there's actually two global minimum points, both here and here, and you'll see that. So the smallest y value is 0, so 0, according to the book's terminology, is the global minimum, and this occurred at two different x values right here. Last example, take a polynomial on the interval negative 1 to 4. Since it's a polynomial, you won't have any problem with differentiability. It's differentiable everywhere, but do take the derivative, you get this. Set that formula equal to 0, factor, and the solutions are x is equal to 0 and x is equal to 2. Therefore, the only two critical numbers are the x value of 0 and the x value of 2. Now get the corresponding y value. So plug in 0 into this formula, you'll get y is 1. Plug in x is equal to 2 into this formula, and you'll get y is equal to negative 3. But these are not the only x values to look at. Step 2 is to look at the endpoint. So look at x is negative 1, look at x is equal to 4, plug those in here to get the corresponding y values. So when you plug in x is negative 1 into here, you'll get y is negative 3. When you plug in x is equal to 4 into this formula, you'll get y is equal to 17. So now just gather together these four y values, 1, negative 3, and 17. Which is the biggest? That's 17. That's the global maximum. Which of these is the smallest? You actually have a tie. You have negative 3 occurring at two x values, both at 2, this 2 here, and also at negative 1. Okay, and you can see all the same stuff in the graph. There are two global minimum points. One is right here, one is right here, and there's one global maximum point right there. Of course, you can do all this stuff even if the function f is not a polynomial. We've stuck mostly to polynomial functions here just to keep things easy and not so tedious, but any function that you can take the derivative of, you can do this, and the extreme value theorem guarantees that closed interval method works. So if you have a continuous function f defined on a closed interval, then you will, using this method, obtain the absolute maximum point and the absolute minimum point.